So here we go. The other day plotted IV of the diode, and we have seen the variation in slopes both in the reverse bias as well as forward bias. For a smaller voltage, we say proportional to QV by 2 kT. For medium voltages, where we normally operate, proportional to QV by kT. At higher currents, I say e to the power QV by 2 kT, and of course then it is resistive. So in general, I can be written as Is e to the power QV by n kT minus 1 when n varies 1 kT. N is called ideality, diode's ideality factor. So it is not very obvious from here, it is also a function of the kind of silicon or germanium or gallium arsenide material you use, essentially band gaps. We have already seen this part, and we see even here constant reverse saturation currents we have observed already by now. We would like to add some more terms, that Y at low biases to get 2 kT terms. Then at very high biases also I will get high current to get 2 kT terms. And in reverse, the current which we have evaluated Is is independent of bias, whereas in reality I do see a slope. So very small slope, and therefore R is very high. Reverse resistance is very high, but high doesn't mean it's infinite. So we'd like to quickly look into this. One major reason why this is happening, if this is your depletion layer, or you call it, say, W is the width of the depletion layer, this is my P side, this is my N side. In deriving those equations so far, we assume that there is no recombination generation term available in depletion layer. This was the assumption we made, that there is no generation recombination in depletion layers. But in reality, this assumption is not valid. So let's do it. Okay, if you say, take case 1 in which the device is forward biased. PN junction is forward biased. Under forward bias case, P is getting positive potential, N is getting negative potential. Holes are injected from P side into N side, electrons are injected from N side into P side, and they diffuse down. However, if there is a depletion layer here, under forward bias, actually it will shrink. Under forward bias, it will actually shrink. And let us say there are traps available in the depletion layer. There are traps available in the depletion layer. We assume traps could be anywhere, and many kinds of their capture cross sections, that is their capture rate will be different. But for simplicity, or the maximum recombination can take place where? When the trap is at the recombination center or mid gap. So assume that all the traps available to you are at the mid gap. Okay, that is at EI. In that case, there will be most hole electrons can recombine. You are injecting holes, you are injecting electrons. Some of them may recombine due to probability of recombination. This essentially means some additional or some reduction currents will be possible, depends on the recombination available. So whatever carriers you thought you are injecting, what was our assumption? All of them reach the other side. Now we cannot say all of them reach to the other. If that is so, we can evaluate the recombination currents, and the way we do it, we write R is equal, recombination rate is equal to CPCN NP minus NI square upon Cp n plus n dash, n plus n dash plus Cp P plus P dash, where n dash and P dash are the carrier concentration if EP or trap level is at the midband or EI. Okay. And N and P of course are related to EFN, EFEV on the either side. So in case this is true, we can always assume right now that N dash is related to EP at EG this, that at the mid gap. At the mid gap, if the trap level is at the mid gap, what is the concentration one says if the Fermi level is at the band gap, half of the band gap? So N dash must be equal to P dash must be equal to Ni. Is that clear? Must be equal to, if they are halfway, the possibility is they must be equal to intrinsic value. Now if that assumption we make and then we write N is equal to related to EF minus EI on the N side and EI minus EF on the P side, what is the difference between the two voltage EF we said? Applied bias, e to the power QA term appeared, that is the difference between the two Fermi level splits is essentially the forward bias. Where will be the Fermi level in N side, higher or lower than P? Higher level. If the Fermi level goes up, then the V0 minus Vf will have band gap, this carrier will be lowered. The opposite, as you said, is fair enough. In the reverse bias, EF will be higher than EN, EFN, and therefore bands will bend much stronger. So this, once you substitute these values, we also assume for the sake of completeness, simplicity right now, Cn is equal to Cp, assume something. We also assume tau P0 is equal to tau n 0 is equal to tau 0, okay. How much is tau? 1 upon Cnt, 1 upon Cnt is the tau. Cn tau, Cn, this n is, Nt is, oh sorry I forgot Nt, that's why. Nt is the number of traps per cc available, so sorry that Nt term mistake. So 1 upon Cn Nt is tau no, 1 upon Cp Nt is tau po. Right now assume Cn is Cp, so tau P0 is tau and 0 is tau 0. Assumption simply, or that's the maximum possible available. We also know, as I said, N is equal to Ni e to the power. What is Boltzmann relation? Exponential EFN minus EI by KT, and by similar logic one can write for P. Substitute this relation here and also you write EFN minus EFP is equal to QVA, and half of that, that is EFN minus EI is therefore QVA by 2. Half of, if the trap is in between, half above voltage, half lower voltage. If I substitute all this, similarly you write for P, in this equation, what I am going to get R, and that's most important, R maximum as I call, because I am assuming everything to suit my this, I get Ni by 2 tau 0 e to the power q, instead of A, since we have been calling F, but the book which I used is the other one, Niemann's book, they are using A, so I think I wrote A, but doesn't matter. Kt minus 1 divided by e to the power QVF by 2 Kt minus 1. You just substitute this, and more detail you can see in the Niemann's book. So this is roughly equal to, if you don't see this, Ni upon 2 tau 0. If I neglect 1, this will go above e to the power q Vf by q. 1 I neglect, then divide. 1 I neglect. Q to the power q Vf by kt is always larger than 1 in most cases, except for very short value of voltages. Even with a smaller value, please remember even at 0.1, 0.2, 40 times that is e to the power 4, 5, and that is not small number, it's roughly 50, 60 numbers. So if I get this R maximum, then what is the way I wrote earlier my generation current, recombination currents? You recollect? J recombination is equal to, where can be recombination can take place? Anywhere in the transition region, anywhere. Perhaps maybe everywhere along the x-axis. So to get the net current, rate I know, Q into rate into dx. If I integrate this Q into R over the total depletion width, which is proportional to voltage under root of that, please remember W. So this value roughly equals to Q Ni W upon 2 tau 0 e to the power q Vf by 2. Is that okay? Just substitute R here and integrate. There is no x term there, so only term will appear is W from the x. So you get Q Ni W 2 tau 0 q Vf by 2 kt. If I now substitute Vf of the order of 0.1 or 0.2 in the other term, which is I is equal to Is e to the power qV by kt minus 1, which is our normal current we said, evaluate Is, okay, evaluate Is and evaluate, of course if you want I, then what should I do? Multiply by area. So if I evaluate this term and if I evaluate this term, I figure out that I recombination may be of the order of 10 to the power minus 7 amps, which is around 0.1 microamp, where I diffusion will be of the order of 10 to the power minus 10 amps. So which is dominating? The recombination current. But if I start increasing the Vf beyond 0.5, 0.6, the second term, that is diffusion term, will start e to the power k will pick up very fast compared to the generation term. So till something 0.4 volt kind of thing, the recombination current will dominate and it will show you a relationship of e to the power qV by 2 kt. Beyond this, the diffusion term starts dominating and you see e to the power qV by kt. That's why the slopes in real life, this we keep saying this is not really Is. Somewhere you feel this should go on, but this is slightly higher than what we actually thought. Okay. This has been tried because we actually fitted that curve into those regions and it did not fit very well. So we say, lower क्यों गया? इसलिए गया. Is that point clear? So this fact that we realized from experiment with a low bias, we figured out that the generation terms, recombination terms dominate at low biases. As bias increases, the diffusion will take over. Now this is if I do the same case for depletion layer, reverse bias, what changes do you expect? हमारे चीफ किधर बैठे हैं? हाँ, let's say I reverse bias. Instead of forward bias, the barrier potential reduced. Okay, so W becomes smaller in fact. Is that clear? Whereas if I apply reverse bias, what will happen? W will increase. Will the field increase across the junction in reverse bias? Both voltages are in the same sense. Built-in voltage and reverse voltage are in the same sense. So built-in voltage plus this means fields is larger in reverse bias, larger electric fields. larger electric fields, please take it from me, if your E is larger, much larger, electrons and holes will experience larger kinetic energy or larger force. Is that clear? So before they could recombine, probably they will be swept off. However, one fact which I should have said, in any semiconductor, at any temperature, there is a constant generation recombination. Is that clear? Everywhere thermal turn will be always present. The other carriers may exceed this value, but generation recombination term is always there. So you are pushing the carrier, actually which carriers will go in reverse bias? Which carriers are moving? Electrons from here will actually go here, holes from N will go towards P, and they are not allowed to recombine. Okay, they are not allowed to recombine. Now this essentially means that there will be some generation term available to you inside. Is that correct? So in the reverse bias case, it is the generation current which will start important way compared to recombination. However, what is generation recombination equivalence is? Minus of R is G. If something is minus of recombination means it must be generation. If I use the same expression as I wrote for R earlier, and how many N and P will be there other than generation terms? N will be 0, P will be 0 because no carriers can remain inside the transition region, they will just be swept off. So we say in the transition region N is 0, P is 0. We'll assume recombination center at the trap levels all at recombination center with NT as their density. Then we can see in the expression which I wrote, just tell me what will be now R. R is equal to PN CP NT NP minus Ni square divided by Pn N plus N dash plus Cp P plus P dash. I already said N dash is equal to P dash is Ni, N is equal to P is equal to 0. Okay. So how much is R I am getting from here? Give me R. Yes. This is 0. This is Ni. So I get minus Ni. Is that clear? This is Ni square and this will give me Ni. Okay. This is 0, this is 0. So I take Ni. Ni cancels. So Ni upon Cn and T plus 1 upon Cp and T. Assuming again that tau's are same, this is essentially minus Ni by tau 2. So in the case of R now, you have a minus R, and what does minus R means? The generation term. So if I substitute this term here, I again get Q Ni upon 2 tau 0 dx or equal to a minus of minus because generation term is minus of this. So this is plus Q Ni W by 2 tau. So does it look constant to you? Q Ni W by 2 tau 0, does it look constant or it is not a constant quantity? W is a function of what? Reverse bias. Larger the reverse bias, larger is the depletion width. That means even in the reverse bias, what we initially thought that IS term, which is QA dN upon ln, that those values are constant independent of bias, in reality these people will show some slope because W is a function of reverse bias. Larger the reverse bias, larger is W. Larger is W, larger is the generation current. This plus the total current is how much? So this should be called J generation. minus of minus, okay. So total reverse current is how much? J reverse is J whatever we get due to drift or diffusion, whatever we call, plus K generation. The first term is constant, okay, constant in the sense independent of voltage. The second term is a function of bias. So even in the reverse saturation case, so why we are so keen to know this? If you see equivalent circuit, the other day I said, what is the equivalent circuit in reverse bias? I said ideally switch should be open. Okay. Ideally what was expected from me? I want something like this. This I was not getting. But I say okay, this has some resistance. So I expected this RR should be tending to into very large resistance because IS is almost constant, so it should be very large resistance. But in reality we figured out that this RR is not that large as we thought, maybe tens of mega ohms. It is not certainly thousands of mega ohms, not giga ohms times. So we figured out in circuit, wherever diode gets this, let's say diode is reverse bias and there is something equivalence of this appear, if this R is comparable, this will reduce the output voltage. Is that clear? If RR is not very large, as it may happen in larger voltages, then in a circuit, it may actually reduce the voltage in a circuit. Is that clear? So diode, ideally if I say use ideal diode, you open it, solve it. You say pseudo ideal means okay, put RR equal to some 1 mega ohm, 100 mega ohm. But in reality, RR may be as 1 mega ohm or so. In which case, depending on the other circuitry part or other load ahead, that output voltage may be a function of diode resistance itself. Is that clear to you? And this fact we need to know in circuits because at the end, how much outputs I'll get when the diode is on and off, I'll be interested in. And therefore, some circuits you already done, I hope, in the lab, Clipper, clamper, something. You must have observed that depends on the load you put, the values may change because of diode getting reverse bias does not mean it opens. This issue is therefore relevant in smaller voltage signals because you always work on small signals. So in small signal that matters very much and therefore you must be aware how much is your RRs and RS. Is that clear to you? This issue is therefore not just for the sake of understanding physics, oh why 2 kT. No, there is a relevance for us. Now before we conclude this part, we want to go ahead and we say okay, reverse bias I have seen, forward bias I have seen. Let's say I am still in forward bias. Depletion width is smaller, but now I have reached relatively much higher currents. What was our theory in diffusion terms? We said that the holes which are injected from P into N, when they reach N, how many numbers we declared there? They are called what? Minorities. In N, holes were in minority. Electrons in P, what were they were? They were in minority. That is, P's of N was much smaller than N's of N0, that is NDs. N's of P0 is much smaller than NHs. This is what our whole theory was based on. However, if you start increasing the current, what does that mean? That the whole concentration at the junction, XNO, and electron concentration at minus XPO is sufficiently large. That's why current is larger. If this number is equal to or closer to NO, that is PPO and NNO, they are no more in minority. Is that point clear? We said they are in minority, but if P's of N is of the order of N's of N0 and N's of P is of the order of P's of P0, they are no more in minority. Okay. Now in this case, if they are not, if you see that expression we wrote, Pn is equal to PNO e to the power QV by KT. If I say PN into NN, if I take multiply of this will become PNO into NNO e to the power QV by KT. But this Pn is equal to Nn from here, so we say it is Pn is equal to, therefore PNO, NNO is Ni square e to the power QV by KT, sorry, Pn square. So Pn is Ni e to the power QV by 2 KT. So at larger currents, the carrier concentration is now e to the power, what was the boundary condition I applied? It is e to the power QV by K, PNO e to the power QV by KT at, what is this boundary condition I applied? At this point, this is the concentration. But now, this concentration is e to the power QV by 2 KT, and if you substitute that in this, your final expression in current will also show e to the power QV by 2 KT term instead of QV by KT. So at high injection levels, you see again e to the power QV by 2 KT terms. Is that clear? Because the minority carrier concentration is similar or almost same that of the majority carriers there. That means this essentially will change into e to QV by 2 KT terms. Boundary condition changed there, and because of that current shows slower rise now. However, if you continue to increase voltage, now we have said already all our theory was based on this, that if this is my V0 initially, okay, at no time Vf reaches V0. That is, all voltages drops across junction and it is never more than V0, only then diffusions probably can occur. Because then only whole electrons can go through the barrier. However, if you keep increasing the forward bias, one expects that Vf may cross V0. That will be a great thing to happen, that suddenly current may be infinite. That is, so itne se volt mein million amps currents can be obtained. तो इतना सब सोलर सेल से लेकर थर्मल न्यूक्लियर पावर जनरेशन का जरूरत है ना, एक डायोड लगाओ और इन्फिनिट करंट ले लो, कितनी पावर. दैट मीन्स दिस इज नॉट हैपनिंग. तो थर्मोडायनेमिक्स इज गेटिंग वायलेटेड. वी सेड क्या हो रहा होगा. तो ऑब्वियसली Vf is never crossing it. So where is the voltage given? I am increasing V out externally. Okay? Internally Vf is not getting beyond V0. तो बाकी वोल्टेज जा कहाँ है? तो बाकी वोल्टेज जो जहां भी जाता है, if this is your, okay, and very high bias, this will be very thin. If you see, if larger current is flowing across this, even if this is not very highly doped, generally there is not, one of them may be heavier doped, there will be I into R related to P region, I into R related to N region. So there will be a current I into Rn plus Rp, which is, this has a resistance equal to Rn, this has a resistance equal to R. How much is this R? How do I calculate R? If I know the conductivity, that is Q mu N, I know the resistance, rho is equal to rho L by A. So by size, I know how much is the resistance of that region. Since I know these values for a given device, this voltage, whatever I applied, actually is equal to Vf plus if I apply larger voltage, Vf also bit of increase, so I increase I. But if I increase I, this value will also increase. So if this value will be essentially, which is across the junction, is applied voltage minus I, R we call it I, total. So larger the Vf, larger is I, this will subtract, okay. So it will try to balance itself at the end, and at no time Vf will cross V0. but the number of carriers at higher biases, VF is increasing, it will be very high, you are crossing even high injection levels. So the carriers on both sides may be almost equal, in which case it will not act like a junction, but it will act like a simple resistor. So you see a ohmic region at the end of it. Is that clear? And huge carriers move both sides, conductivity is very high, is that clear? So it acts like a simple resistor, low value. This is essentially what happens if the current is exceedingly very high. Is that clear? So have you now clear that the regions which I started with, in real life, IVs are not same as what first theory suggested, ideal theory. But ideal theory, why we want it? Because we always believe, and which many times correct, what is the physics way of doing it? Perturbation. Some function is there, usko perturb karo. What does that perturbation word means? It cannot exceed the value itself, otherwise it's not a perturbation, it's a change. So all our theories are still based on basis that these are smaller effects compared to the main effect. If someday it finds that they are comparable or larger, then this whole theory has to be revisited. But as of now, we didn't find anything different. So we believe that this relationship which we obtained, and therefore this is a relatively good relationship. Only thing is, in the case of reverse current, this should be taken as a function of bit of VR. It's not constant, so it is not really too high as I am showing. You can see from here, the slopes I showed are still not very, they are not zero kinds, but they are not very large slopes either. The RRs are higher, but certainly not as high as I. Okay, now the last effect which I am interested about junctions before I leave this. Okay, maybe before that, one more interesting part I can show you. If you see please look at it. If I show my eye in the forward or reverse, I find it is a function of Ni, it is a function of what else? dP, dN, whatever you call it, and it is also e to the power qv by 2 or nkt kind of terms. All these terms are functions of temperatures. All these terms are temperature dependent. Ni, what is Ni? NCNV e to the power Eg by 2 kt. NCNV is under root 2 pi n star kt 3 by 2 pi. So again T terms there. So all these terms, Ni, Dn is mu is related to temperatures, 3 by 2 or 2 by or minus 3 by 2 law it will follow. Since all these terms are temperature dependent, I is a function of if you see even the reverse saturation current which I just wrote, QA Dn NPO upon Ln plus QA dP PNO upon LP, this is 1 I reverse plus QNI pi tau to 0 into W. This is temperature dependent, this is temperature dependent, even this because this is Ni square by Nd or Ni square by Ne. These are temperature dependent terms, and into of course e to the power Qv by Kt or Nkt term is further temperature dependent. But in reverse bias that term can be neglected because e to the power minus Qv by Kt is smaller than minus 1, so we neglect that. So at least for reverse saturation current, these terms will show you larger reverse current. Is that correct? Everything will increase. So if the device starts heating, then the reverse saturation current also starts increasing. Now what is the problem? If the reverse saturation current increases, anything? Look at a circuit or a device. Just tell me, if you have a circuit and you are using it for longer time, it will start getting heated. So what will happen? Its reverse saturation current will increase. So this forward current also increases, Is to the power, e to the power. So both forward current and reverse current will increase. So if you are using this as a switch like a bipolar transistor or a MOSFET, then in either on-off status the currents are higher. What is off state we call? When no current flows. But now this no current business is not no current, it's a real current business. And if that happens, the device does not remain switched off. Because if the reverse bias and the reverse off state, if the currents are large enough, that means it's conducting. It means it is not in an off state. Okay. So whole your microprocessor logic or any hardware may not function if the temperature starts rising sufficiently. The maximum temperature up to which device probably can operate, can you think from where it will come? I just said you, Ni is a function of temperature. Okay. If Ni value reaches the equivalent value of N or P, then it is no more junction, Ni is Ni. Is that clear? So junction property will be lost at a given temperature when Ni matches closer to your dopants. Is that correct? And this does not occur at very high temperature. Around 175 degrees centigrade, Ni rises enough that you figure it out that no more junction properties can be maintained. So the maximum temperature up to which circuits can operate is 150 degrees centigrade. Okay, 150 degrees. Why we are interested in 150 degree higher temperatures? Because in satellites or in the say tanks or any rockets or anything, they may be placed in either Himalayas or they may be placed in Rajasthan desert. The temperatures can rise, external ambient is very high. So what is the problem if the temperature outside is higher and inside is much higher? So is the rate of cooling proportional to what? The difference. Is that clear? This makes, that means it can't be easily cooled. Is that clear? So the device gets heated even if you want to cool it. Or you put liquid nitrogen there, perhaps, so that it picks up. But that means extra money and extra so much. So we do not wish to go beyond certain temperatures. So all devices are marked for minus 55 to 150 degree or preferably 125 degree centigrade device must operate. Is that clear? That's the range in which device can operate as a device. Beyond that, device will not operate as a proposed device. Is that clear? So that is why if you see any, I don't know any time you see, but data sheets, devices are specified with temperature ranges. So beyond that, the performance will degrade or not even work out. Is that clear to you? So one method people suggest is to somehow reduce this off-current. How do we do that? That's all technology and that's all funda ahead in other courses. How do you reduce reverse currents? Having said so, an interesting thing I can show you. If I have I versus V at some temperature T1, and I actually heat this wafer for another temperature, diode at another temperature, which is larger than T1. I see IV moving towards left, larger currents at lower bias. That's what IS says. Now can you think this is something interesting device I made if I see something like this? Okay, I take a circuit in which this I0 is fixed, current source. Current source means current doesn't change, that's why it's called current source. So in a diode, I force a current I0, is that correct? At this two temperatures, I can monitor V2 and V1 from the IV characteristics. I can just measure the drop. Okay. So I know V1 and V2. V1 minus V2 or V2 minus V1 is proportional to V2 minus V1. So what is this device is? Thermometer. It's a temperature sensor. A diode can act like a temperature sensor. Is that clear? Change in temperature is proportional to change in voltage. So I monitor voltage. I know it's a It's proportional. That constant I can find by measurements or by calculation. I can even directly, you know 2 equations, 2 unknowns. I can always evaluate that. This is essentially a thermal sensor. So diode acts like a thermal sensor. Typically 2.3 milliamp per volt, millivolt per amp is some change one can observe in the device. This is typical and not necessarily true for all devices. So I can figure out at a given temperature, per degree. So how much temperature, how much voltage should have shifted, I know very well. Is that clear to you? So one technique, as I say, thermistors use is this. Thermistor actually is a resistor many times. But many of the thermistors have diodes, which is calibrating diode as they call, and they use this theory. Is that clear? So I just want to tell you that diode has almost 600 applications. Not one. 600 applications. I am giving you a few of them. Some other day, some other times. Okay, so this this takes care of temperature effects, which is very much important for us. Before we quit junctions, the last part, which is not very small part, so far we always assume that DC voltages are applied, V plus, minus, DC. In all circuits, who cares of DC? DC तो एक capacitor लगाया तो खत्म, आगे ही नहीं कुछ हुआ. So we are not very keen always to work on a device which is only DC device. But DC has advantage, but you cannot say that DC diode will be only act like a DC device. In reality, you will always have a signal. But where that signal should be applied will be decided by what DC you are actually applying on the device. So for example, if you see this IV characteristics, IV, and let's say this is my IV, at this point is my VG, which I applied to the diode. And now, on this, I superimpose the AC signal. This is what will happen. In real life, AC signal and you will have biased it. You have done this experiment already. So you have a DC which is biased and over which you are applying an AC signal. So what is it trying to show you? As long as, okay, let's say these are the two values corresponding to the peaks of this. We now see that if this signal magnitude or amplitudes are very small compared to VDC, that means this peak signals are much smaller than the net value of VDC, this can be treated as decline. If they are larger, then the slopes may appear, but if they are very small, we say they are almost a straight line. And if I take the slope of that line, di by dV, what is this di by dV will be? 1 upon resistance of conductance, G. So what do? If I apply a small signal AC, this resistance which I am actually getting is the AC conductance. Is that correct? What is DC conductance will be? I by V. Is that correct? But what is AC conductance? di by dV. Slope there. But it is a function of at what voltage I apply. Because at some other point, this will be different. Is that correct? So where do I bias the diode has relevance the value at what value R will get. But for same V, DC, R is known to. Is that can be AC resistance, is that or AC conductance. Is that AC clear from where it is coming? Because I apply a small signal which is we can say as a phasor e to the power j omega t, then I figure it out that small change will result in a equivalent of slope there, which means AC resistance. So diode has equivalent of AC resistance. If I want to find this, I assume I is equal to Is e to the power qv by kt. One I neglect, and then I write VDC plus V bar e to the power j omega t, or right now assume VAC for the sake of this, by kt is e to the power qVDC by kt into e to the power qVAC by kt. How much is this current? IDC. DC. Okay. And this, if VAC by VDC is much smaller than 1, that is small signal values if you choose, this can be expanded as 1 to the power qVAC by kt. Is that clear? So how much is the AC current? This is DC plus AC. Any total current is DC plus AC. So AC current is IDC Q VAC by KT. If I do VAC by IAC, it is KT by Q IDC. But this is nothing but RAC. So this so-called GAC value you got is QIDC by Q. Since IDC always can be found for the DC value you apply, so to get an AC resistance you don't need to know any other thing except the condition which I wrote, that the small signal must be attained. If you do this, QI by KT is G or KT by QI is. So let's take a small case. Let's say IDC is 1 milliamp. How much is R for 1 milliamp? KT by Q is 25 millivolt by 1 milliamp, roughly 25 ohms. Is that clear? So I can always evaluate the R of a diode, ACR. Please remember AC. Why I am interested in AC? Because the circuits which I am going to use will be all mostly AC dependent, signal dependent. And because of that I would like to know how diode behaves under AC signal. DC I have studied. But I figure out that at the end the DC value is deciding the AC value. And that's very great about it. So you only have to know the DC parameters, and that is why what is DC parameter in a device we call biasing conditions. So the biasing condition decides the AC performance. This is very interesting. The DC biasing conditions actually decides the AC performance. Is that clear to you? Is that clear? So this is very relevant, that why people are worried about where do you bias, because I have just shown you. If I put IDC, VDC somewhere else, R will be different. If I do here, it will be different. Because if there is continuous linearity, that but it's an exponential function. Okay. So obviously at what VDC or IDC you use, the R's will be different. So one must know what is your biasing point. Okay. That is why we say in circuits, or when the device is put, which is, how do you bias it? Okay, that will decide the performance. All AC parameters which you see later, that is transconductance GM, or the output resistance, or the input impedance, or whatever we call, all are AC values, but decided by their DC value. Is that clear? So at the end of the day, yes, the circuit is more relevant if we know its AC equivalent rather than DC. What is the DC equivalent? I said RF, RR. But in the case of this, we must know what is equivalent of this. We like to derive next time before we do this. This is what I am going to get. RAC you call it, EJ, R. This is the equivalent circuit of a diode. RAC shunting by R. Now this, do you get the point? Something I am putting here, under forward bias, this term will vanish. Okay, this RJ, CJ will vanish. In reverse bias, only capacitive resistive effect. Okay, RJ, CJ. RJ is how much? RR. How much is that will be? Tens of mega ohms. CJs will be of the order of few picofarads. However, in the forward bias, I just calculate RAC, I must evaluate this term CD, which is called diffusion capacitance. Is that clear? Diffusion capacitance. Forward bias. What did we think in the reverse bias? Junction capacitance. Now in this case also there is a junction capacitance because depletion there will reduce, so CJ will be still higher. Okay. Doesn't matter. Because that will actually, if higher means 1 upon omega C is, so that will not be very crucial for us. But this above one, diffusion capacitance will very crucial for us. What for this diffusion capacitance can come before I quit? Can anyone suggest? What is the cause of this diffusion capacitance in forward bias? No, what you said is correct. If I am injecting holes and I am injecting electrons, for a fixed value this PNO is constant, PNO e to the power QV by KT is constant for a V value. But if I apply VAC on this, plus VM minus VM, so PNO is also function of plus above and lower above. If PNO value changes at XNO, then what will it change? The currents. Is that correct? Or charge. Change in charge, change in voltage is a capacitance. So even in the forward bias under AC signals, you will get some capacitance which is called the diffusion capacitance. Next time we'll evaluate this and finish the diodes and start with, hopefully this may not take more time, just 2 minutes. We'll start with MOS capacitors. Please start thinking of chapters which teach MOS capacitors.